In this video, we will cover the basics and go into practical detail on RC high-pass filters. To do so, we'll look at some theory, going through the maths, but then also looking at the time domain, frequency domain, and some practical considerations when you're sizing RC high-pass filters. To help us do this, we were using function generators and oscilloscopes, as well as this power supply filter demo PCB, which will be upcoming in various other videos as well. Here we can place different capacitors, resistors, series and parallel elements, and then examine their properties. The PCB you can see in the top right, which has already been messed with quite a bit, that's why it looks a bit rough, is what we'll be looking at and using to inspect RC high-pass filters in a practical sense. Throughout, and also at the end of this video, we will look at some practical implementation of RC high-pass filters, not just in the sense of a demo PCB, but where they're used in the real world and how you might size them yourself. I also have a video on RC low-pass filters, which goes into quite a bit of depth, and that's video number 118 on my channel, and I'd suggest watching that before you continue on with this video. A huge thank you to Altium for sponsoring this video. Make sure to check out the link in the description below, or go to altium.com/YT/PhilsLab, and you can get yourself an Altium Designer free trial, as well as 25% off your first license purchase, and you can check out all the cool features, including Altium 365. Please visit the link in the description below to learn more about Altium 365 and many of the cool features, such as ECAD, MCAD integration, library management, design reviews and markups, and much, much more. Octopart is also a part of the Altium ecosystem, so make sure to go to octopart.com, which allows you to search for millions of components across hundreds of component distributors very easily. A huge thank you to PCBWay for sponsoring this video. The power supply filter demo PCB was manufactured by PCBWay, as well as the blue digital signal processor PCB was also manufactured and assembled by PCBWay. I'd highly suggest you check out their services. They've got many cool advanced services such as FPC, Rigid Flex, as well as advanced PCBs which I use quite a lot, including HDI, buried and blind vias, and any specs you could possibly dream of. You've probably already seen RC high-pass filters in many different designs. The basic structure can be seen in the top left image. We have an input voltage from an input voltage source, which feeds into a series capacitor, and then we have a parallel resistor at the output where we take the output voltage. This is the most basic RC high-pass filter structure we can have, and we'll see alternatives, maybe higher order filters, in this video as well. Oftentimes, this structure might be a bit hidden that it's an RC high-pass filter, depending on the circuitry. For example, in the top middle, we have an RC high-pass filter in the form of AC coupling. We have C404 and R406 forming our basic RC high-pass filter, but this high-pass filter is to separate or remove DC bias between stages. Then, for example, on the right side, we have a band-limited non-inverting amplifier, and the RC high-pass filter is a bit more hidden. In fact, it's a combination of C415 and R416, very simply speaking, that will form a high-pass filter. RC high-pass filters might also appear, for example, in audio, in tone controls. And this is taken from a really great website, sound-au.com, as a typical tone control or equalizer circuitry. And you'll see there are many RC combinations that actually act as high-pass filters. So in this video, I'd like to show you the basic RC high-pass filter, its performance, its characterization, and how you can design them into your own systems. As was the case with the RC low-pass filter, we will first of all examine the RC high-pass filter in terms of a potential divider. A typical potential or voltage divider we can see at the top right-hand side, where we just have two resistors. We feed in an input voltage and take the output voltage at the center point between these two resistors. This potential divider reduces the input voltage, both AC and DC, by same fixed amount across all frequencies. The RC high-pass filter, however, we take the top resistor and replace it with a capacitor. You can see a capacitor, very simply speaking, as a frequency-dependent resistor. So it has a reactance instead of a resistance, and its reactance or resistance is inversely proportional to the frequency. So the higher the frequency, the lower the reactance of the capacitor, and the lower the frequency, the higher the reactance of the capacitor. Therefore, we've transformed our potential divider into a frequency-dependent potential divider. A term we will look at quite often in this video is called the gain, which is the ratio of the output voltage divided by the input voltage. And for the RC high-pass filter, as was the case with the RC low-pass filter, this is frequency dependent. Without any math analysis, we can ask ourselves two questions. What happens when the frequency of Vin is very low? So let's say a sine wave at the input. What do we get at the output? At DC, basically, C is an open circuit, and therefore we have Vout is pretty much zero. Conversely, when the frequency of Vin is very high, so a high AC frequency, a high AC sine wave, C is effectively a short circuit, and the output voltage is pretty much equal to the input voltage. So already we can see this filter probably, as also the name suggests, lets high frequencies pass and blocks low frequencies close to DC. This is a passive first order filter, and there are variations of this, of course. Some use cases, as we saw before, are for example to AC couple signals, remove DC offsets for filtering, tone shaping, and so on. What we will consider in this video is look at the time and frequency domain response, but then also look at practical considerations, such as what influences the choice of R and C, for example, values, tolerances, dielectric types, and so on. How do we set cutoff frequencies? What about cascading filters, loading and source effects, and much, much more. Let's start off with a time domain analysis. So for a given time-varying input voltage, Vn of t, how does the output voltage, V out of t, change over time? I want to see how this depends on R, the value of resistance, and the value of capacitance, C. For now, we will also assume we have an ideal voltage source feeding this RC high-pass filter, series resistance, completely ideal source, and an ideal load where we're measuring from, for example, a very, very high impedance scope probe. Then our usual circuit analysis techniques, we know that the current through C, our capacitor, is the same as the current through R, our resistor. We go through our Kirchhoff's laws, so I equals C dV by dt and V equals IR, set the currents equal, and then we arrive at this differential equation. So the output voltage plus R times C times the rate of change of output voltage with respect to time is equal to R times C times the rate of change of input voltage with respect to time. Already from this differential equation, we can see we only get an output voltage if we have a change in input voltage over time, which hints at that for a DC input, we don't get any output or 0-volt output, and only for AC signals, we will get some sort of voltage at the output, again indicating that this is a high-pass filter. This differential equation is a first-order differential equation, and this means we also have a first-order filter. We simply have one reactive element, which is our C here, so this is what we expect. Then we want to look at a couple of responses. For example, the step response, where we feed in, as you can see in the bottom right-hand side, a step starting at some low voltage, a rising edge to some sort of high voltage. And the response to that is called the step response. Given this first-order differential equation, the solution is expected to be exponential, and we can see that in the far bottom right-hand side. Effectively, it's a decaying exponential. Initially, with no change in the input signal, we don't get any change in the output signal. Then at this fast rising edge, we have an AC signal, an AC stimulus, meaning this is passed through the capacitor, so we also get a pulse on the output of our RC filter. But as the input voltage settles again to a new DC value, we can effectively see the capacitor discharging into our load. So again, the AC signal, the rising edge, is let through, whereas the DC signal is eliminated after some time. This after some time part depends on R and C. There's an RC time constant, which is effectively just R times C, and that will change the speed of decay in our output voltage waveform. Again, we have a time constant rule of thumb, so the approximate decay time from 90% to 10% of the step is about 2.2 times R times C. So for very large resistance and very large capacitance, our decay time will be much, much longer in comparison to a short time constant, so small R and C values. We can plot a solution to this differential equation quite easily using a graphing calculator for a step response. Let's say a step response with a 1 volt peak input at t equals 0. So at t equals 0, the output will jump to 1 and then decay down to 0. If we change the input voltage magnitude, of course we change the output voltage magnitude. But if we change the time constant, this RC time constant, we can change the decay time. So if I increase R, we can see it takes longer to decay. And if I increase C, it takes longer to decay. The multiple times R times C gives hint and rise to the time constant and tells us the rate of decay. Now let's examine this RC high-pass filter in the time domain in the real world. To do this, we'll use this demo PCB. I've soldered in a capacitor, which is 100 nanofarads in series, and at the output a parallel resistor, R, which is 22 kiloohms. And we'll need that to form our RC time constant. I feed in an input signal from a function generator and also measure the input signal. At the output, I also attach an oscilloscope probe to measure the RC high-pass filter response. To help me perform the measurements and analysis in the real world, I'm using the Analog Discovery Pro by Digilent. So I'm using 2 oscilloscope channels, one for input and one at the output for the RC high-pass filter, and one of the WaveGen channels to generate my test signal. Remember our time constant rule of thumb, and this will be important when we look at the real-world results. So 2.2 times R times C. So plugging in the values, 2.2 times 22 kiloohms times 100 nanofarads, and just converting that to milliseconds gives us a time constant of about 5 milliseconds. With this in mind, let's go over to the waveform software. I've hooked up the test equipment as shown before, and let's feed in a square wave at a frequency of 50 Hz, amplitude 1 volt, offset 1 volt, so we get a 0 to 2 volt square wave, so with rising and falling edges. Then going over to the scope, this is channel 1. The yellow channel is the input to the RC high-pass filter, where we have our square wave voltage form. So we have a DC signal at 0 volts, then we have a fast rising edge to 2 volts, DC signal, falling edge, and so on. Now let's look at the output of the RC high-pass filter where the voltage is taken across the output resistor. And this is channel 2, the blue channel. And this is pretty much what we expect to see if you remember back to our step response analysis. On the rising edge of the input, so our yellow trace, we also get a rising edge at the output of the RC high-pass filter because this is a fast AC transient which passes, very simply speaking, through the capacitor directly and charges up the capacitor. Once we hit the DC signal, effectively since it's a high-pass filter, we don't let any DC signals through, so we get a decay back to our 0 volts at the output of our RC high-pass filter, and we get this decaying exponential response, effectively our capacitor discharging. Similarly, on the falling edge of the input signal, so this yellow trace, the falling edge, we get a very similar response, except it's mirrored. We get a negative output voltage at the output of our RC high-pass filter. So falling edge, and then decaying exponential back to 0 volts, our DC signal. Remember, our time constant was about 5 milliseconds, so let's see if this holds true. I'll add just a quick measurement, and this is fairly rough. Remember, this is about 10 to 90%. If we look at what 5 milliseconds is about, which was our 2.2 times RC, we can see this encapsulates most of this decay time of our falling output at the output of the RC high-pass filter. So this is why we have this RC time constant. We can also change our square wave to a sine wave now. We'll start off with a frequency of 10 kHz, an amplitude of 1 volt with 0 volts offset. Sine waves are great because they're effectively just a single frequency component, which is the fundamental of the sine wave, and we can compare the input sine wave to the output sine wave. Given that this is a linear system, we will expect to see an output which is also a sine wave. Now the output sine wave, which we'll also see in the frequency domain response, will have changes in phase and magnitude. So for a 10 kHz input sine wave, which is the yellow trace again, we can see the output in blue, which is the same signal. So for a fairly high frequency input signal, and we'll see what high frequency means later on, we get pretty much the same AC output signal at the output of the RC high-pass filter. Let's say I add in a DC offset, then go back to the scope. We can see the input signal yellow has an offset, but the output signal in blue doesn't have an offset. This is a high-pass filter. We remove DC offset after some transient. Again, removing the offset and now decreasing the frequency of the input signal. Let's see what happens. We go down to 1 kHz. Then look at the output. We can really start to see the magnitude might have changed just a tiny bit, but importantly also we're getting a change in phase. So we're getting a phase shift in the output signal compared to the input signal. If we further go down in frequency of our input signal, closer to DC, for example 100 Hz, we can see the amplitude of the output signal, again blue, has dropped quite significantly, but also we have a phase shift relative to the input frequency. And the closer we get to DC, of course, so this is a 10 Hz input, the larger the phase shift we have, so we have an almost 90-degree phase shift and a considerable drop in amplitude at the output of the RC high-pass filter. Us just having experimented with various sine waves of different frequencies, we've already hinted at the frequency domain analysis and frequency domain performance of an RC high-pass filter. When we're concerning ourselves with frequency domain analysis, we are effectively asking ourselves, how does the gain, so again the ratio of the output voltage to the input voltage, change with respect to frequency depending on the component parameters, so R and C in this case. Again, we're assuming ideal source and an ideal load for now, and we're applying a sinusoidal input, B in, with a fixed amplitude and a fixed frequency. We're expecting a sinusoid at the output because this is a linear system, and we're measuring the sinusoid of the output. We compare the amplitude of the output sinusoid to the input sinusoid, and as well as the phase shift of the output sinusoid to the input sinusoid. Now we can do this as we just did, experimentally, logging values and then drawing a frequency response, but we can also do this analytically from our previous differential equation where we apply the plus transform, and I won't go through the maths here, but the output result is that we get the gain, so the ratio of output voltage to input voltage, dependent on frequency, is this complex term here. So we have this j times 2 pi frc term at the top, and this 1 plus j times 2 pi frc term in the denominator. The reason we have complex numbers, again, is because we have magnitude and phase. And we can plot magnitude and phase on separate diagrams, and together those are called Bode diagrams, which we can see on the bottom right-hand side, which is actually a Bode diagram of our RC high-pass filter. And we'll have a small play around with that in just a second. What we can see on the x-axis, we have frequency. On the y-axis on the top graph, we have magnitude in decibels. And on the bottom graph, we have the phase in degrees. Looking at the magnitude first, we can see on the top right-hand side, 0 dBs is a gain of 1, so we get no attenuation, and that's for sufficiently high frequencies above a certain cutoff frequency. Below a certain cutoff frequency, we can see we have this downward slope, which is effectively attenuation. So negative dB values means a gain less than 1. So as we go closer and closer to 0 Hz, so DC, we get more and more attenuation. So we get less and less of that output signal given a certain input signal. And this is where we get this high-pass filter response. So high frequencies are passed on the top right, and low frequencies are effectively attenuated or blocked at DC. The phase performance is also important, which you can see just below this graph. So at sufficiently high frequencies, we have a phase which is close to 0. At a crossover frequency, we have a phase of about 45 degrees. And at low frequencies, so close to DC, we have a phase shift of about 90 degrees. So again, important is we have pretty much infinite attenuation at DC. Before a certain cutoff frequency, we have this minus 20 dB per decade roll-off. Then we have a fairly flat, so 0 dB gain in the passband. This isn't a particularly great filter. It's not particularly sharp, fairly slow roll-off. It has limited attenuation, but it only requires 2 components, so very simple to implement. We already hinted at the cutoff frequency, which we can see on the bottom side here. This is known as the minus 3 dB frequency, and where we effectively have a half power bandwidth. And this is how we typically define bandwidths of filters. So what is the frequency at which our magnitude in dB hits minus 3 dB? And the same as for low-pass filters, for high-pass filters, the formula is F equals 1 over 2 pi R times C. We can actually plot the magnitude very simply, again using a graphing calculator, for a simple RC high-pass filter. I can change the values of R and C, and I can plot the gain either linearly or in decibels. So linearly in the top in red, frequency is on the x-axis, linear, and on the y-axis in the red trace, we have a linear gain, so reaching from 0 to 1. At DC, we have a gain of 0, and at higher frequencies, this tends to 1. Whereas the dB scale, which is this green trace, at DC, low frequency, we have a gain of minus infinity, and at high frequencies, we have a gain that tends to 0 dB. So let's just look at the dB scale for now. As I increase the resistance, so I increase R and C, remember 1 over 2 pi RC is my cutoff frequency. We can see the cutoff frequency is this blue vertical trace. As we increase R times C, the cutoff frequency decreases. So I can do that with R, and I can do that with C, or I can do that with both. Zooming in, again, the cutoff frequency is where the magnitude plot hits minus 3 dB, and this is known as the bandwidth of our filter. So we can say effectively frequencies above the cutoff frequency are passed, and frequencies below the cutoff frequency are attenuated. Now, this is very loosely speaking because actually our passband really only looks like it starts in this certain case, let's say above 25 Hz for this particular filter. Attenuation already starts at around 10 Hz, even though the cutoff frequency is defined far lower. This is something you need to be aware of with these very simple or slow roll-off filters. Now let's use the minus 3 dB frequency, so our cutoff frequency calculation, to figure out what our cutoff frequency should be for our 22 kilo ohm resistor and 100 nanofarad capacitor high-pass filter. So that's what I've typed in here. So 1 over 2 pi times 22 kilo ohms times 100 nanofarads gives us a cutoff frequency of about 72 Hz. Let's see if this corresponds to the real-world measurements. The Analog Discovery Pro, along with the waveform software, has a really cool feature known as this network analyzer, where we apply an input stimulus, measure the input, measure the output, and the software will automatically measure the gain and phase for us. So we can let this run, for example, from 5 Hz to 100 kHz with a test stimulus amplitude of 1 volt, and just do a single measurement. So after our measurement, we can see the characteristic RC high-pass filter frequency domain response, which is effectively, again, a Bode plot of the system. The top curve, we have our magnitude. So on the y-axis, we have gain in decibels. On the x-axis, we have the frequency in hertz. The bottom graph shows us the phase. Again, frequency in hertz on the x-axis and phase in degrees in the y-axis. So at very low frequencies, close to DC, this is measured down to 5 Hz. We've got quite some bit of attenuation. So at 5 Hz, we have about minus 27 dBs of attenuation with a phase shift of plus 90 degrees. As we then go closer and closer to our cutoff frequency, remember, we calculated this to approximately 72 Hz, our phase shift nears 45 degrees. Keep in mind, we have component tolerances and non-idealities, which will play into the results. After the cutoff frequency, so around 72-ish Hz, we then move into our passband, where we have effectively 0 dBs of gain and fairly flat, and a phase shift that is close to 0 degrees. Taking a very rough measurement, we can see that for these particular components, our cutoff frequency is actually just about 100 or slightly above 100 Hz. And again, keep in mind the capacitor might have a 20% tolerance, the resistor might have 5 or 10% tolerance, and these will of course influence the cutoff frequency, as we'll see later as well. Another quite interesting aspect to RC high-pass filters is that they can act as fairly crummy or band-limited differentiators. Remember from the frequency domain analysis, looking at the plus domain, we saw that the gain relationship was given as this equation on the top left, rewriting that S equals J omega, or S equals J 2 pi f. We can see this is S times RC over 1 plus SRC. So effectively, it's an S term, which in the Laplace domain is a differentiator, times this RC over 1 plus SRC term, which is a low-pass filter. So a differentiator followed by a low-pass filter gives us a band-limited differentiator. Because the differentiator frequency response is like so for this increasing gain characteristic with a constant 90 degrees phase shift, we add to that in the log domain a low-pass filter, so passing low frequencies, and then we have this high frequency cutoff. We add those together, this cascaded system, we get our RC high-pass filter, so a band-limited differentiator. This means if we stay in this slope domain, so far away the cutoff frequency to the left-hand side, very simply speaking of the cutoff frequency, we get derivative action. So if we, for example, pass in a triangle wave, we should get a square wave out. If we pass in a sine wave, we might get a cosine wave out, and so on, as long as we're far below the cutoff frequency of our specific filter. Keep in mind that there's also quite significant attenuation below the cutoff frequency, so the gain will be scaled as well. So for our specific RC high-pass filter, we had a cutoff frequency of around 72 Hz in the ideal case, so we should stay far below that for our input signal fundamental frequency. Then going to waveforms, let's say I have a fundamental frequency of 20 Hz and I'd like to do a triangle wave as my input and see if the output resembles somewhat of a square wave. So I've started that, and looking at my output, we can see yes, the input is the yellow curve, triangle wave, so the derivative of that is in the ideal case a square wave, and this is what we get at the output in the blue case. Keep in mind, attenuated by quite an amount because we're far below the cutoff frequency. We can also change this to a square wave with a fundamental frequency still of 20 Hz, and we can see the output resembles impulses at the rising and falling edges, which is close to what we expect for taking a pure derivative. Keep in mind this is a band-limited differentiator. And for example, for a sine wave input, we will expect a cosine wave output, so same frequency but phase shifted by 90 degrees, and that's what we get. As is the case with pretty much any electrical system, we have to also consider source and load effects. Previously, we said that we are connecting an ideal source, which has a zero series resistance or zero source resistance. Pretty much any non-ideal source will have some finite output impedance. In this case, we'll assume it's just a series output resistance, RS. So the gain we have to now consider is effectively Vout relative to Vs, which is our source voltage. In addition, we'll also connect our RC high-pass filter to some sort of load. This might be a transistor amplifier, an op-amp, or a high-impedance buffer, but in any case, this load will have some sort of finite input impedance. And in this case, we can just assume it's a parallel input resistance, RL. Working through the math, we get this equation with a gain which is dependent on frequency, and we can see a couple more terms have appeared. First of all, as is quite obvious from the picture as well, R is now in parallel with RL. So if our load impedance is very, very high and R is comparatively very small, then of course R will dominate and the parallel combination won't change very much. But if R and the input impedance of the load are similar in magnitude, then of course the parallel combination will be quite different. Or if RL is very much smaller than R, then of course RL will dominate. Similarly, we also see that RS appears now in the equation as well. In effect, RS, the source impedance, and the load impedance, RL, will introduce a shift in cutoff frequency. It'll change the overall impedance versus frequency, and also RL and RS will ensure that the AC gain, so at high frequencies, is not equal to 1. Even though C might be a short at high frequencies, effectively, RS, R, and RL still form some sort of potential divider. And if RS is comparatively large compared to the parallel combination of RL and R, then of course you'll get some attenuation even at high frequencies. Again, the solutions are as usual, so keep the source resistance fairly small and keep the load resistance fairly large comparative to the components you're using in your RC high-pass filter. Of course, there might be better options than using a passive filter. You could use an active filter with active elements to isolate the filter even more or feed it via low source impedance and so on. We can, of course, also, as with low-pass filters, cascade stages. This might be to improve the frequency domain performance because we can pass the signal through multiple stages of the RC filter structure, and the number of stages is effectively the order of the filter, and we can vary, of course, the R's and C's within these parts of this cascaded filter. Now, the returns aren't that great for passive filters, and you probably might be better off starting to use active filters such as VCVS, Sallen-Key, and so on. What we can also do, as we've looked at low-pass filters before, is cascade high-pass filters with low-pass filters to form a bandpass filter. And that's what you might see in the bottom right-hand side, where we have a low cutoff frequency and a high cutoff frequency, and we only let a certain band of frequencies through. Again, we have to consider many things: the frequency domain performance, roll-off, cutoff frequencies, time domain performance, if we get delays and phase shifts. And again, I'd like to illustrate complexity and performance versus an active filter. Oftentimes, an active filter might be the better choice compared to cascading filters. What we also saw in the measurements is that component non-idealities had quite an effect on the cutoff frequency and performance of the filter. For example, the resistor, we might have a certain tolerance. This might be 1%, 5%, or even worse. And of course, that'll have an effect on the impedance seen by the source, as well as the cutoff frequency. As the cutoff frequency was f equals 1 over 2 pi RC, as R varies for a fixed C, then of course f will vary. Similarly, for a capacitor, we have a tolerance which might even be worse, so 10 or 20%, and again, that'll affect the cutoff frequency in a similar manner. Capacitors are also more problematic typically because, especially for class 2 multilayer ceramic capacitors, we have things known as bias and derating. I'll skim the basics in this video, but I'd strongly suggest checking out video number 114 on my channel, which goes all over hardware design basics with ceramic capacitors. Bias and derating means, for example, for certain types of MLCC multilayer ceramic capacitors, that applying a DC voltage will significantly change the capacitance, or a different temperature might change the capacitance, or even a different AC voltage stimulus might change the capacitance. I've taken some figures from Murata's sim surfing tool, which is a free tool where you can explore all of these parameters, and for example DC bias characteristics, temperature, or AC voltage, and you can see there's quite significant capacitance change depending on various external factors. So make sure you take those into account when you're choosing your R's and C's. Also, the actual type of capacitor, so if it's a ceramic, what type of ceramic, what the dielectric is, if you're choosing an aluminium electrolytic, a tantalum, a film, and so on, all of these capacitors might have different properties. They might have different maximum allowed voltage ratings, better bias and derating characteristics, but some of them might also introduce nonlinearities or have piezoelectric effects, such as class 2 multilayer ceramic capacitors, which introduce distortion. So some capacitors you might want to have in your audio path signal chain, for example, class 2 MLCCs, and you might use a film capacitor instead. Finally, before we look at some practical examples, let's look at some more practical considerations. While this is less of a concern with the high-pass filter than it was with the low-pass filter, we still want to be sure that, for example, at high frequencies, when the capacitor appears effectively as a short, that our source can drive a combination of RS plus R in parallel with RL, which will be our lowest impedance. Again, we have to consider what effect the load will have on the impedance, gain, and cutoff frequencies, and also what the source effects might be. When it comes to choosing the cutoff frequency for the specific application, again using the formula f equals 1 over 2 pi RC, we have to remind ourselves that passband was not flat, and this is especially true close to the cutoff frequency. So we might want to choose the cutoff frequency slightly lower or slightly higher depending on where we want the attenuation and where we want our passband to be. You also have to consider not just the gain, but also the phase shift. If you're doing very particular measurements, or you have somewhere where phase is critical, you want to stay away from the cutoff frequency and be well into the passband to ensure that you have close to a 0-degree phase shift at high frequencies. Once you've figured out what cutoff frequency you want, of course you have to choose specific R and C values, so you have effectively 2 more degrees of freedom. Again, this is situation dependent. If you choose a lower resistance value, which in turn for a fixed cutoff frequency means you need a higher C, this will give you overall a lower impedance at high frequencies. But then again, the loading, so RL, might have less of an effect, which is a positive, but then in turn you will need a larger size capacitor. Larger size capacitors might come in larger package sizes. You might be limited in the type of capacitors you can use. For example, you might have to use class 2 multilayer ceramics because they have a higher capacitance density, so to speak, and so on. Conversely, if you use higher resistance values, that will give you lower Cs. So using higher resistances will give you higher overall impedances. Loading might have more an effect if you have a small RL, but then again, you might be able to use smaller size or more different types of capacitors for your C value because you've increased your R. Lastly, let me show you some practical real-world examples where I had to implement RC high-pass filters and how I sized them and chose them. For example, for this Xerxes PCB, also manufactured by PCBWay, which is effectively a mixed signal PCB with a Spartan 7 FPGA, some memory and control interfaces, as well as an analog section, which then feeds a codec, so an ADC and DAX, where I can do digital signal processing on the Spartan 7 FPGA. In the audio section, I've had to use several RC high-pass filters for various reasons. So looking at this in Altium Designer, for example, the analog input section, this specific system is for guitar, so I require fairly high input impedances and an AC coupled system. So my guitar comes in at an input jack, feeds into an RF filter, and then I have my first RC high-pass filter comprising of C301 and R302, followed by a buffer. R301 and R302 at AC, when C301 is effectively a short, will form the input impedance of this device. So it'd be 1 meg in parallel with 1 meg, so it's a 500k input impedance, given that this U301 op-amp is a very, very high input impedance amplifier and effectively negligible. Therefore, my combined R is the source impedance, so 68 ohms with whatever my source impedance is, with my load impedance, which is 1 meg in parallel with 1 meg, with my series capacitor C301, which is 10 nanofarads. From that, you can then figure out the cutoff frequency. The cutoff frequency is fairly high because guitar only extends down to maybe 100 or a couple hundred hertz, and therefore I could keep C301 small and have a large input impedance governed by R301 and R302. That's why I chose R large in this case and C small, because I want a large input impedance, I want to minimize loading effects, and I want to keep my capacitor small so I can use type COG input capacitors that only come in small packages. Also, I follow this by an active non-inverting buffer to mitigate loading effects which come due to the second order filter stage after this input filter. Not only does this input filter serve as to define a lower bandwidth of the system, but also for AC coupling. Because I'm biasing these op-amps at half the supply voltage, because I'm using a single rail supply, I need to bias my op-amps at half the supply rail, and I don't want any of that leaking out to my guitar or to whatever plugged in before this. So therefore, I'm also using this high-pass filter to remove the DC offset to separate DC biases. Thank you very much for watching this video. I hope it is useful and I hope it showed you how to implement RC high-pass filters in your own designs and how to analyze the time and frequency domain performances of these systems and also what to take care of in a practical sense. If you like the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any embedded system and hardware design videos. Thanks again for watching, and I hope to see you in the next video. Bye-bye.